Welcome back. So in the previous lecture we have seen that instead of giving physical values in the Simulink model, we can reference it with some variables and then define variables in the workspace. So the issue with this method is that each time we run the simulation, suppose you make the simulation, you close it, then next time when you open it, you'll have to type all these things once again afresh. A better solution is to use a script. A script is a MATLAB file which will run before the Simulink starts, and it will have all these parameter values. So once it runs, it will load the workspace with these parameter values, and once then Simulink runs, Simulink will not find any problem and it will not find any missing data and it will run smoothly. So I will show that. Just click new script. So this is the editor. So type in whatever you want here, your array, which is in 0.5, which is in ohms. Okay, the percentage symbol stands for the comments. So whatever comes after that in this line, the compiler of the MATLAB will ignore it. So you generously use comments to give visibility to your program. Ra is in 0.5 ohms, La is the armature inductance, which is in 0.1 Henry or 100 microhenry. 100 millihenry. Then we have moment of inertia of 5. In kilogram meter per second square. Viscous friction coefficient 0.01. The load torque, let it be 50 Newton meter. Armature voltage 160 volt. Tau armature is given by La by Ra. Tau mechanical time constant given by J by B, and K5 is 1.6. That's it. Now you can just save this. The extension is .m. Give motor parameters. Any meaningful name. I am saving it with motor parameters. Parameters. .m. Now let's clear the workspace. Now see, the workspace is blank now. Now just you have to open the script motor parameters.m, run it. Some error. What is it? Line 6, column 7. Oh, sorry. Yeah, you cannot give V here. Just mention it is volts. Yeah. Now it should run. Yeah, the motor parameters, that file has run and it has loaded the workspace with all these parameters. So you need not type it again and again. Once you open MATLAB, just run this file, then open Simulink. That's all. So the Simulink file is already there. Yeah, just run it. Two changes I have done in this lecture especially. TL I have made it into a fixed value 50 and I have made it into 160 volt as the armature voltage. Now let's run it and see. Yeah, we have seen it. Initial inrush of current contributes to this much amount of torque, then it comes to steady state within approximately at 5 seconds. The speed is around 850 rpm. Now we have seen if I reduce the value of armature voltage, naturally speed should reduce. Earlier it was around 900 rpm. Now see, it has come down to, and it is settling at around 620 rpm or something of that kind. Even then torque remains at 50 because our load torque is 50. This is not 50, it will be slightly more than 50 on account of the friction losses. See, 50 is here, it is approximately 51. Clear? Same way, if I go to higher voltages, 200 volt, the speed should go above 1000. Let's see. Naturally, you see, this is 1000 and it is gone above 1000. So whatever we have studied is been validated using simulations. It will be interesting to know what will happen if torque changes, for which we will use a step change. That is, torque has some value and at some time it changes its value in a step manner. Yeah, go to sources, common Simulink, sources, you will find step change, step here. You drag it here, we will use this. Now if you double click this, you will see the step time, which means at what time the step must be implemented. Our simulation runs for 15 seconds, let it run at 8 seconds. What is the initial value? Let it be 15 Newton meter. At 8 seconds, what should it change to? Let it change to 75 Newton meter. Or let it be 25 Newton meter, let it change to 75, let it change to 75 Newton meter. And I will remove this. Now what I have done, I am applying a load torque equal to 25 Newton meter from 0 second to 8 second, and exactly at 8 second, this 25 Newton meter changes to 75 Newton meter. Let's see what happens. Yes, see, it has settled at 25. At 8 second, it jumps to 75, and this is reflected in speed change. As the torque increases from 25 to 75, the speed drops from 920 to approximately 840 or something of that kind. Remember, when I taught in class, I told an increase in load will always be accompanied by a decrease in speed. That's what you are seeing. Similarly, if I reverse it from 75, if I am dropping the torque to 25, you will see a jump in speed. That you can try it yourself. Now we have seen the change in torque, change in speed. Now let's see how does a step change in armature voltage look like. I am removing this. I will give a step change in voltage. Let the initial voltage, let the step change happen at 5th second or 6th second. So I mean, let it be 8 seconds itself. So that steady state has happened. The initial value is, let it be 160 itself, and the voltage reduces to 100 or 120 at 8 second, and let it be a constant torque load. Let it be 25. This is load torque. Now what happens is that we are applying an initial voltage of 160 volt to the motor, and at 8 second the voltage drastically or in a step manner it will changes to 120. So what do we expect? The speed should fall at 8 second. Let's see whether it is happening. I am running the simulation. Yes, see, at 8 second this waveform has much more to explain. At 8 second, speed has reduced from 160 volt, it has gone down to 120, so speed has reduced. There is nothing to explain in this, but see the torque equation. Torque, after inrush, it settles at this value. At 8 second, what happened? The voltage has reduced, thereby a negative torque is being developed. 0 is this, so this much area is negative torque, or the motor is braking, and that's seen here. When braking operation happens, the speed of the motor falls. Is this clear? I hope it is clear. You can play with these values and see. So we have seen changes in TL as well as armature voltage. Another parameter which we can change is the moment of inertia, for which let me remove the step kind of a load. I apply 160 back. What was my J here? J was 5. Initial value of J is 5. So it takes approximately how much time to settle? Let me zoom in along this direction. Let's say it settles in 4 seconds. It settles in 4 seconds. Imagine what if I change the value of j. J was 5, I changed it to 10. Naturally, what we should expect is, see, j has changed to 10 from initial value of 5. 5. It should take more time to settle. Let's see whether it is happening or not. Earlier it took around 4 to 5 seconds. Yeah, let's zoom along. No much change. Let's increase j further. I think j is not getting reflected here. Yeah. Okay. The issue, I understood the problem. See, I am changing j, but tau m is not getting changed. Tau m still remains at 500. So let me update tau m as well. Sorry, tau is equal to j by b. See, initial value was 500. Now it has changed to 5000. Let me see how does it affect. Sorry, run the simulation. Oh, it has not. Yeah, it has come here. 500 has changed to 5000. Let's see what change do we have. Yes. See, 15 seconds is not enough for this machine to reach steady state. Naturally expected. J has increased from 5 to 50. Let me give it a little more. Instead of, I will give it a 10 itself. 10 tau for m is nothing but j by b. So from yeah, it has changed. Now let's run it again. 5000 will change to 1000. Hope it has a settling time within 15 seconds. Now earlier it took 4 seconds. Now it is settling somewhere here, close to 8 seconds. Naturally, as expected, as the moment of inertia of the load increases or the motor system increases, it takes more time to reach a steady state. So like this, you can change all these parameters and see how does the motor behave. So make your own model, play with it, have a deep understanding and insight of how a DC motor works to changing disturbances. All the best.